OCR Physics, and this is my third video on thermal physics, and it's about the thermal properties of materials. So this diagram, you should know this from very early on in your education, and it's basically the particles in a solid and in a liquid and in a gas, in a typical solid. So look at this, going from a solid to a liquid, that's called melting. Going from a liquid to a gas, evaporation. Going from a gas to a liquid, condensation. Going from a liquid to a solid, solidifying. It does actually say in your specification that you need to be able to describe what's going on in a solid, liquid and gas. So, you know, I mean, revision of stuff you did in year 7. In the solid, the particles have fixed positions. They can't move around. There is a regular arrangement, usually. They are vibrating, so they have some kinetic energy. They are vibrating. And of the 3 of them, this is where they have the least energy. If you cool down the solid so that the particles, you know, if you got to absolute 0, then they would just be sat there doing nothing. In a liquid, there is no regular arrangement. There is no crystalline structure, no lattice or anything, no regular arrangement, no fixed positions. The particles can move around. And what happens is they're kind of jumping from one bond to another. So they're kind of changing places and they are moving around. Bonds are continually being broken and made. And this system has more energy than the solid. Note that the particles are not further apart in a liquid. In fact, for water, they're actually closer together, which is why ice floats, because it's less dense. In a gas, the particles move independently and randomly, and they're whizzing around very fast. They've got, well, most of them on average have lots of kinetic energy and they're whizzing around very fast. They're actually banging into each other a lot as well. They are much further apart, and this system has the most energy. So be able to describe the arrangement and the energy, the motion of the particles in a solid, liquid and gas. Okay, and as we go from a solid to a liquid to a gas, the internal energy of the system increases. Now, properties, thermal properties, there are 3 of them that we need to know. You've got your specific heat capacity, you've got your specific latent heat of fusion, and specific latent heat of vaporization. Specific means per kilogram, okay? Specific heat capacity, the energy needed to raise the temperature of a kilogram by 1 degree centigrade, or 1 Kelvin, because it's the difference, yeah, you're raising the temperature. So E equals MC delta theta. I prefer in OCRB we say MC delta T. There's that new wrapper in the MC delta T. But anyway, E equals MC delta theta, and little c is the specific heat capacity. Specific latent heat of fusion, that's the energy needed to melt a kilogram of a substance. And then the specific latent heat of vaporization is the energy needed to evaporate a kilogram of a substance. And that's just E equals ml. And it's either LF, which is fusion, or LV, which is vaporization. So these are the 3 properties we need to know. This experiment, you may have to describe this experiment. Hopefully you've done it. And it's to find the specific heat capacity of a solid. And we use an aluminium block. So you've got a 1 kilogram aluminium block, and it's got a couple of holes in it. One of them is for a thermometer, one of them is for a 12-volt immersion heater. That goes in there. Obviously that's connected to a power supply. You've got loads of insulation, a lid as well, and you've got a timer. So you let the heater warm up. You measure the voltage and the current so you can work out the power. You insert the thermometer into the insulated block and you record the temperature. Then you insert the heater and then you measure the temperature of the block after 10 minutes. That's one way that you can do it. That's the way that I usually do it. Measure the temperature of the block after 10 minutes. I don't see the point of measuring it every minute and drawing a graph. It's just pointless. Okay, have a go at this question here. Yes, pause the video, pen, paper, calculator, should be dead easy, and the answer is that. Okay, 1,210. So, joules per kilogram per Kelvin, or per degree centigrade. Now, if we look in a data book, we actually see that it should be 900, the specific heat capacity of aluminium. Why is our answer bigger than that? And how would you change the experiment to get a better answer? Yes. And how would you modify it to find the specific heat capacity of water? Well, the reason that our answer is bigger is because we are losing energy to the surroundings. Not all of the heat energy is being given to the aluminium. Yes. And maybe the aluminium block isn't being heated evenly. So there are several reasons, but basically not all of the energy is evenly being given to the aluminium block. To do it for water, to find it for a liquid, basically you just put it in a beaker of liquid. Again, make sure it's insulated, make sure anything electrical is insulated as well. Now, this is another experiment that hopefully you should have done. Now, it's usually done with something called stearic acid. And stearic acid, at room temperature, it's a solid, and it has a melting point of 69 degrees centigrade. So what we do is you put it in a boiling tube or a test tube, and you heat it up to about 90 degrees so that it's all a liquid, and you've got a thermometer in there. And then you take it out of the water bath and you let it cool down, and you measure its temperature every minute as it's cooling down, and you plot a graph of temperature against time, and we get this graph here. Okay, so look at the temperature against time. So you've got your liquid cooling down, but as we get to 69 degrees, then the graph levels off. So we've got a horizontal line, and then after a while it starts cooling off again. And you should understand this graph and understand what's going on. If you did the experiment, your graph may not be as perfect as this one. This is a bit idealized, but there you go. So what's going on? Why is it this shape? Well, basically, to start with, we have a hot liquid cooling down. So it's losing energy to its surroundings, and it's just basically cooling down, temperature's getting less. On the horizontal bit, we have a mixture of liquid and solid. This is where it is solidifying, which is happening at the melting point. And what's happening is that we're still losing energy to the surroundings, but what's happening is that bonds are forming. So the particles are joining together as it becomes a solid, and this is releasing energy, and that energy is being given off to the surroundings. Then after that, when it's all a solid, then it just cools down again, a hot solid cooling down. So mixture of solid and liquid, this bit in the middle is what we're really interested in. Bonds are forming between the particles. Energy is released to the surroundings at constant temperature. And the energy released as the bonds form is called the latent heat of fusion. And here's a little question for you to have a go at. Pen, paper, calculator. Do this question. 3, 2, 1. The answer is... There you go. Now, consider this. This is a beaker of water, and we've heated it up, maybe with a Bunsen burner or some kind of electric heater, and it is boiling. So we've got boiling water. Now, here is a graph of, first of all, we are heating up the water, and then when the water gets to 100 degrees centigrade, the graph levels off and the temperature stays the same. Now what's happening here is that it is absorbing heat, but the heat energy it absorbs is used to break bonds. So energy is absorbed at a constant temperature as bonds are broken between the particles. Have a go at this question. The specific latent heat of vaporization of water is thingy, blah, blah, blah. The answer is in 3, 2, 1. There you go, about 3 kilowatts.